So in this section, we're going to see more about the basis stuff. And more specifically, we're going to see that choosing a coordinate system makes a vector space look like Rn. So let's begin with the theorem number 1, the unique representation theorem. So suppose that you have the basis B, which is given by this. And then for any element x in V, then we can write x as the linear combination of the basis vectors. But the theorem states that this representation is unique. So that is to say, the weight C1 through Cn are unique. So let's quickly prove this theorem. So first of all, we know that the basis spans the given vector space V. Then this means that for any vector x in the vector space V, we can write x as a linear combination of vectors in B. So say C1 times B1 plus so on until Cn times Bn, where C sub 1 through C sub n are just a real number. And suppose also that there is another representation d1 through dn such that x is a linear combination of vectors in B with weights d1 through dn, so something like this. Then our goal is to prove these coefficients are actually the same thing. So if you subtract 1 from 2, then this gives you, well, on the left hand side we have x minus x, and on the right hand side we have c1 minus d1 times b1 plus so on plus cn minus dn times b sub n. Or in other words, we have 0 equals to c1 minus d1 b1 plus dot 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 plus cn minus dn times b sub n. But we know that vectors in basis are linearly independent, which means the given vector equation has only the trivial solution. So we have c1 minus d1 equals to 0, c2 minus d2 equals to 0, and so on, and cn minus dn equals to 0. Or in other words, we have c1 equals to d1, c2 equals to d2, and cn equals to dn. So in conclusion, there's a unique way to write x as a linear combination of b1 through bn. Suppose that a set of vectors B is a basis for a vector space V, and x is an element of the vector space. Then the coordinates of x relative to the basis B, or simply the B coordinates of x, are the collection of weight C1 through Cn, such that x can be written as a linear combination of vectors in B. So in this case, sending x to B coordinate is called as the coordinate mapping, where the square bracket x sub B is given by the collection of the weight of that linear combination. And we call the square bracket x sub B as the coordinate vector of x relative to B, or simply the B coordinate vector of x. So let's look at this example. So suppose that you have a set of vectors B and E given in this way. So they form a basis for R2. And suppose that you took the vector x, which is given by 6, 5. So to find the B coordinate of x, well, first of all, we have to write x, which is given by 6, 5, as a linear combination, say c1 times 3, 1 plus c2 times 0, 1. Then the solution for this vector equation is given by, so if you let c1 equals to 2 and c2 equals to 3, then you can check that if you multiply 2 into the first vector and 3 into the second vector, and if you add them together, we get 6 and 5 on the left hand side. So in this case, we can tell that the B coordinate for x, which is the collection of these coefficients 2 and 3, so the B coordinate of x is given by 2 and 3 in this case. On the other hand, for E coordinate, we can decompose 6 and 5 into 6 times 1, 0 plus 5 times 0, 1. So if you collect the coefficient of this linear combination, then the E coefficient for the given vector x is given by 6 and 5. So here you can tell that when the basis is given by the standard basis, then the coordinate vector for x is the same as the original vector x, which is given above. Okay, so let's see the geometric interpretation of the coordinate. So the idea here is that the coordinate system defines a one-to-one mapping of points into a set to Rn. So before we see the graphical interpretation, let's pause the video and try out part A and part B for this example. Okay, so let's solve these two problems. So suppose that the B coordinate of x is given by 2 and 1. Then we want to find the coordinate representation for the standard unit vectors. By definition, this gives you that the given vector x can be written as the linear combination of the vectors in B, which is given by 1, -1, and 1 and 3. And the coefficient for these two vectors here and there are given by 2 and 1. So you can fill in the blank by 2 and 1 in this case. Or this gives you, I guess, 3 and 1. On the other hand, to find the E coordinate, you want to find the coefficient for this linear combination. But we know that we have to put 3 over here and 1 over here to get 3 and 1. So this gives you the E coordinate of x is given by 3 and 1, which is the same as the vector over here. Next, suppose that you have the vector b, which is given by -2 and 8. Then to find the b coordinate for this vector, we have to find the coefficient or the weight for the linear combination in terms of the vectors in b. So let's say -2 and 8 equals to c1 times 1 and -1, and c2 times, say, 1 and 3. Then if you consider the augmented matrix associated with this vector equation, the matrix is given by, I guess, 1, -1, 1, 3, and -2 and 8. And then if you do the REF of this augmented matrix, I guess we can simply add the first row to the second row. Then this gives you 1, 1, -2, and 0, 2, and 3. So this gives you 2c2 equals to 3, or c2 equals to 3/2, c1 plus c2 equals to -2, or c1 equals to -2 minus 3/2. That gives you -7/2. So for this reason, the b coordinate for the vector b is given by -7/2 and 3/2. Okay, so let's plot all the results that we got from part A and B. So basically the vector x is given by 3, 1, which is over here. Oops, I forgot -2, negative sign over here. So the vector b is given by -2 and 8, which is located over here. And for b coordinates, so we know that the set b is given by 1 and -1 and 1 and 3. So these two vectors are here and there. Then if you form axes that contain these two vectors, like extending these two vectors, something like this. And let's mark the unit as the magnitude of the basis vector inside B. So we know that the B coordinate for x is given by 2, 1. So if you keep track of that information, so 2 is over here and 1 is here. So if you go over by 2 and go up by 1, then we get the point x. And at the same time, -7 over 2 is somewhere over here, I guess. And 3/2 is located at here. So -7 over 2, 3/2 again gives you the same vector b as well. So geometrically, we can tell that these coordinate vectors give us the coordinate with respect to the grind system that is formed by the given basis vectors. Now, we're going to talk about how to work around the different kind of bases in Rn. So suppose that B is the basis for Rn and P sub B to be a matrix formed by the vectors in B, then P sub B is called as the change of coordinate matrix from B to the standard basis Rn. And this is because this vector equation is equivalent to the given matrix equation. So you can observe that if you write this as the matrix product, then X is given by B sub 1 through B sub n times the weight of linear combination C1 through Cn. Then you probably want to write the B coordinate of X as the P sub B inverse times X, right? But is this always possible? Or equivalently, can we always find the inverse matrix for the change of coordinate matrix? Well, I guess the answer should be yes, because we know that the vectors in B are linearly independent. And second, P sub B is n by n matrix. So what does this remind you? We can apply the invertible matrix theorem to show that there exists the inverse matrix. Okay, so let's practice with this example. So suppose that B is given by these two vectors and X is given by 6, 8. Then we can tell that P sub B, which is the change of coordinate matrix from B to the standard basis, is given by the matrix of the column vectors of B. So 3, 1, 0, 1. Then we can easily calculate the inverse matrix of B in this case. So I think the determinant of P sub B equals to 3. So it should be 1/3 times 1, 3, and 0 and -1. So multiplying this matrix into the vector X will give you, so the B coordinate of X is given by the inverse matrix of P sub B times X, which is 1/3, 1, 0, -1, 3, multiplied by 6 and 8. And I guess it is 1/3, 6, and 18. That gives you 2 and 6. So the B coordinate of X equals to 2 and 6. In general, if you have a arbitrary vector space V and B be a basis for the vector space V, then the coordinate mapping that sends the vector X into B coordinate is a 1-to-1 linear transformation from V onto Rn. So in other words, V is isomorphic to Rn. So let's prove this theorem. So we first have to show that the given coordinate map is a linear transformation. So suppose that you took two vectors u and v in large V, then we can write u as the linear combination of the basis vectors that is given by this. And also we can write v as a linear combination of these vectors. And here, c sub i's and d sub i's are numbers for I is 1 through n. Then this tells you that the B coordinate of u plus v equals to c1 plus d1 through cn plus dn, where if you separate c's and d's, then this gives you the sum of two vectors, something like this. But indeed, this equals to the B coordinate of u plus the B coordinate of v. So you can separate the addition. And also, if you multiply some number p to u and then take the B coordinate of this vector, then this gives you pc1 through pcn. Or in other words, we can factor out p outside of the matrix or the vector. Then that gives you, well, this equals to p times the B coordinate of the vector u. So this tells you that the coordinate map x to the square bracket x sub b is a linear map. Furthermore, this map is 1-to-1 because, so if you let the B coordinate of U and V's are the same, then this tells you that C1, B1 plus so on plus Cn, Bn equals to D1, B1 plus so on plus Dn, Bn, because C sub 1 through C sub n are the same as D sub 1 through D sub n. Or if you move this to the left hand side, then this gives you C1 minus D1 times B1 plus so on plus Cn minus Dn times B sub n equals to 0. Or in other words, this tells you C1 minus D1 equals to 0 and the Cn minus Dn equals to 0 because B sub i's are the basis for the vector space V, which means they are linearly independent. Or in other words, we have C1 equals to D1, C2 equals to D2, and so on, Cn equals to Dn, or equivalently, we have U equals to V. And for on2, so if you take any element, say y1 through yn inside Rn, then we can form a vector in V as a linear combination of b1 through bn with its weight y1 through yn. So it is given by y1 b1 plus so on yn bn. And this is the element in V such that the b coordinate of x equals to y1 through yn. So this tells you that the given coordinate map is on 2. And in conclusion, that gives you 1-to-1 and onto map from V to Rn. So let's consider the standard basis for P3, which is given by 1t, t squared, and t cubed. Then polynomials in P3 behave like vectors in R4, and this is because, well, if you let this one to be P1, and this one to be P2, and this one to be P3, and the last one to be P4, then we can write any polynomials as C0, P1, C1, P2, C2, P3, and C3, P4. Then the B coordinate of X becomes, I guess, C0, C1, C2, and C3. And in this case, we say that the vector space P3 is isomorphic to R4. So this problem is about verifying the given set is linearly independent using the coordinate vectors we have defined above. So basically, these are polynomials of degree at most 2. So we can regard this as an element of R3 such that, so the first row corresponds to the constant term, and the second row corresponds to the coefficient for t, and the last one to be the coefficient of t squared. Then we can write p sub 1 as E coordinate, which is given by 1, -1, and 0. And p sub 2, E equals to 2, -1, and 1. And p sub 3, E, I guess 0, 2, and 3. Then these three vectors are linearly independent if and only if the matrix formed by these three vectors has pivot position for each columns. So if you RREF this matrix, I guess we can do that by adding the first one to the second row and divide the last row by 3. Then that gives you 1, 0, 0, 0, 1, 0, and 0, 0, 1. So we can conclude that columns are linearly independent. Consider a set of bases B, which is given by two vectors in R3, and H to be a vector space spanned by these vectors. And we want to find the B coordinate for the X given by this way. So by definition, if you write X as a linear combination of B1 and B2, then X square bracket B would be C1 and C2, and we have to find these two numbers. So if you write this as the matrix equation, then this gives you 9, 13, and 15 equals to 3, 0, 3, 1, 1, 3, C1 and C2. So because we have 3 by 2 matrix, to solve this matrix equation, so we have to RREF the augmented matrix associated to this matrix equation. So the augmented matrix is given by 3, 3, 1, 0, 1, 3, 9, 13, and 15. Then if you subtract the first one from the second one, and then if you divide the first row, and then you subtract that one from the last one, then that gives you, I guess, 103, 0, 1, 4, 0, 3, and 12, or this is row equivalent to 103, 0, 1, 4, 0, 1, 4, or you will get 103, 0, 1, 4, 0, 0, 0. So this tells you that C1 equals to 3, C2 equals to 4. So the B coordinate for X is given by 3 and 4.